Good evening, young people. Today we're going to be doing Covalent Bonding 3 lecture, and we're going to be talking about Lewis structures, this idea that we're representing covalent bonds and how we model what a covalent bond looks like and what's really happening. Okay, so I'm going to go ahead and get rid of my face so I don't block anything. So the things we're going to understand here is using Lewis dot structures to show bonds in a covalent way, and determining if bonds will be single, double, or triple by using some information about the number of bonding sites that we're going to have and the octet rule for the number of electrons that every atom needs to have. So covalent bonding, it's basically a bonding model. What we're talking about when we say a model, we know covalent bonding is sharing of electrons, and we're just trying to figure out what that looks like. Well, we can see it in multiple ways. You see this way down here at the bottom where we see this idea of a structure here, and we have different viewpoints where we have things coming out in different directions. That's one way to model. And we have three other models here. We have the model up here at the top that's just a stick model that's very common. Notice that there's no C, but that means that there's a C. Here we have another kind of idea, a stick model that looks very similar to this. And then this is called the space filling model. This is actually what it looks like in terms of the sizes of atoms if we were looking at it on the scale that we see it here. So all of these models are things that we use to help us understand what's happening to these covalent compounds. And all of them have limitations. All of them have some strengths. And all of them give me some information. And so they're all also based upon this idea of Lewis structures. So the rule, I've given you some rules in class about how it's done, but I want to give you a little bit further about how we determine bonding sites. So hydrogen and the halogens only have one bonding site. That's because hydrogen only needs one electron to get its 2. Remember, hydrogen doesn't need an octet. The halogens only need one electron to get its 8. Any of them, fluorine, chlorine, bromine, and iodine, are all the same. So what we know is hydrogen and the halogens will only form single bonds. Okay? So they will form single bonds. I'm sure that'll come up in just a second. Oxygen and sulfur have 2 bonding sites. Nitrogen and phosphorus have 3 bonding sites. And carbon and silicon have 4 bonding sites. When we look at that, what it says, I was reiterating here, up here, when we have the fact that there's only one bonding site for hydrogen and the halogens. Now, because there are 2 bonding sites, I'm sorry. Let me back that train up. Because there's only one bonding site, the hydrogen and halogens can only form single bonds. They will never form anything else. So if you have to form a double bond with hydrogen or a halogen, that can't happen. It will never happen. Oxygen and sulfur and its group of nonmetals have 2 bonding sites. Excuse me. One, that means we can form single bonds, we can form double bonds, and we can even form triple bonds if they're needed. Nitrogen and phosphorus have 3 bonding sites. And again, this idea of bonding sites is based upon their valence number. What is the valence of nitrogen? It's 5. That means it needs 3 electrons to be shared. Therefore, it has 3 bonding sites. And so that leaves it with a multitude of possibilities as well for what's going to happen, single, double, or triple. And carbon, again, has 4 because it's got valence of 4, and it can have singles, doubles, and triples as well. I have the yawns going on, I'm sorry. So those are kind of some rules about bonding sites and how we know what's going to form what. Pretty much, if it has more than one bonding site, it can form any kind of bond, double, single, or triple. They are rare in some cases, like 2 bonding sites. Triples are a little bit rare, so we won't see those quite as often in oxygen and sulfur, but they do exist. So Lewis structures. The Lewis structure shows the valence electrons and how they're arranged in the molecule. So we take that idea of valence and we put it together and we try to see how it's arranged in the molecule. It reflects this idea that the compound has to have stability. It has to get to the noble gas electron configuration by achieving an octet, sharing the number of electrons that it needs. So shared electron pairs are the covalent bonds and are represented either by two dots like you see here or a line. You might see it like this. So if I had a bond between H and O, I could represent it with two dots like that. Or I could represent it with an O and an H like that with a line. Those two things mean exactly the same thing. So we're going to look at water here. So we're going to make oxygen the central atom. The reason oxygen is the central atom, there's only one of them. There are two hydrogens. Hydrogen's usually not a central atom. Also, I want you to notice that hydrogen here, hydrogen right up here, has an H first. And we say, oh, that's an acid, but water isn't really an acid. We'll talk about that a little bit later because it's got something there that's kind of interesting, but typically we don't talk about it as an acid. I am sorry with the yawns. Okay, so we start looking. O has 6 valence electrons, H has 2 valence electrons, and there are 2 of them. So we kind of know what's going on. But if we really wanted to calculate it, it's pretty simple. The calculation starts like this. We're going to add up the valence electrons. So O has 6, H has 1 each. There are 2 of them. So we have a total of 8 valence electrons. So when we start putting things together, we start to see, oh, hang on, there are some empty spaces right here in O. So maybe I can put them there. Okay, so we know that there will be enough electrons to complete an octet because there are 8. If you have fewer than 8, you got a problem because you don't have enough electrons to complete an octet. And I think I need to get rid of myself again. Okay, so why does hydrogen not need an octet? It's in the first energy level, and a duet is good for it. It gets to helium, so that's okay. So then we start to join the atoms together. So we have oxygen there. We join it with hydrogen. The first hydrogen, we join it with the second hydrogen. And here we have the dot structure for water right there. Okay? So are all the necessary octets complete? Let's see. H has 2 each, so we see each H has 2 electrons right there. And right there. And O has 2, 4, 6, 8 electrons. So everybody now has 8 electrons available to them. So what if we had the structure CH3Cl? Now this is in binary, and this is called chloral methane. Not sure if I spelled that right now that I'm looking at that. I don't think that O is right there, but it's called chloromethane, okay? So how do we draw this? Well, first we have to start with what we know. We know we have an H, we know we have a C, and we know we have Cls. In fact, we have 3 H's. So let's go ahead and start adding up the number of electrons. What are the available electrons we have here? 4 from the carbon, 3 hydrogens with 1 each, and 7 from the chlorine. We have a total of 14. So we definitely have enough to make everyone, well, we have enough for an octet. We have to have at least 8. Okay? So now, carbon is going to be the central atom. Carbon is usually always the central atom. If carbon is in the compound, it's probably the central atom, or it makes a backbone as a central atom. All of them together, chained together. Okay, so we have this. So the central atom wants 4 electrons. So it looks like I can probably give 1 of each of the hydrogens to one of the sides of the carbon, and that fills it. Okay, so will there be enough electrons to complete everybody's octet? Let's see. So carbon, we join the hydrogens right there around the carbon, and we notice carbon still needs 1 electron to be shared, and chlorine also needs 1. So chlorine comes in and shares its 1. So now let's double check. Each hydrogen has 2 electrons, 2 and 2. Carbon has 2, 4, 6, 8, and chlorine has 2, 4, 6, 8. So everybody has an octet. Okay. Are all the necessary octets complete? The answer is absolutely. We just counted that just a few minutes ago. Okay, now we want to talk about something called diatomic molecules. Diatomic molecules are special kind of molecules that we need to talk about. to remember the elements that form diatomic molecules. See, a diatomic molecule is simply this: a molecule that's formed by a covalent bond with two atoms of the same kind. So what elements, and there are 7 elements on the periodic table that always form diatomic molecules, that you will never find them as single atoms anywhere. And there's a mnemonic device that we need to remember. I call it Brinkelhoff. It's an old good German style name. Yeah, it's really not real. It's just something that we use to remember. And so what does it mean? Br means bromine, I means iodine, N means nitrogen, Cl means chlorine, H means hydrogen, O means oxygen, and F means fluorine. So if we can remember Brinkelhoff, we know the 7 elements on the periodic table that always form diatomic molecules. That is a molecule bond, a chemical bond between 2 atoms of the same thing, 2 atoms of the same element. So we can see where we get Brinkelhoff from. You can see the letters in red that highlight, so we can get Brinkelhoff to understand that better. So let's start with fluorine. Fluorine, we know, has this electron configuration. And we know for fluorine to be happy, it needs to become like neon. And so because it needs to become like neon, each one of them need 1 electron. So those 7 valence electrons are very helpful. So we have fluorine with 7 right there, and we have another fluorine with 7. And notice if one fluorine shares 1 electron and the other one shares its electron, now we see that every one has 8. We see this fluorine has 6 over here of its own. I'm trying to find my pen. We got 2, 4, 6 of its own, and then right here we have a pair that's being shared. That's 8. Here we have 2, the pair that's being shared, 4, 6, 8. So we meet our needs here with the diatomic molecule of fluorine. And we also know there's only 1 bond, a single bond there. That's interesting. So oxygen. Oxygen, we know, has 6 valence electrons. So we see oxygen here, and what we know is going to happen is that oxygen is going to rearrange its valence electrons. And what we're going to end up doing is sharing 2. Each oxygen is going to share 2 of its valence electrons. And when that happens, I have 2, 4, 6, 8 with the 2 shared from the other oxygen. I have 2, 4, 6, 8. And both oxygens now have access to 8 electrons. I will remind you, it's access. They're looking for access to the electrons, okay? So this only could have happened by double bonding the oxygens. We have to take the oxygens and double bond them. That's the only way that that's going to occur. If we just put a single bond there, the oxygens are not fulfilled. They still need an electron. So that makes sense to reform them and each of them to share 2. Nitrogen, a little bit more tricky. Nitrogen has 5 valence electrons, which means they need 3 more. Okay? They need 3 more. So when we start looking at nitrogen's electron configuration, it has 5 valence electrons. So what nitrogen will do, it will share 3 of their valence electrons with the other nitrogen. Yeah, if you're sharing 3 for each, 2 of them sharing 3, that's a triple bond. So what we see here is we have these 2 electrons, 4, 6, 8 here. We have 2, 4, 6, 8 for the other nitrogen. So we see an example of a triple bond. When we started out, though, we started out like this. And then we get the other nitrogen, and it comes in right here, and we've got the nitrogen here, 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 and here. Nitrogen is not satisfied. It needs 2 more electrons. So it makes sense that these 2 electrons will come over and be shared, and these 2 electrons will come over and be shared to get everybody to be an octet, and we see that that is actually the truth. So hopefully you've gotten a better understanding of this idea of Lewis structures, and that will help you gain some more knowledge.